In this video, we are going to talk about reactors of different types in series. Now, it is always not the case that you are using only a system of mixed flow reactors or only a system of plug flow reactors. Okay. It may be so that you have a mixed flow reactor first, okay, and then you follow it with a plug flow reactor, drawing a tubular reactor over here, and this in turn is again followed by a mixed flow reactor. This can be a case, right? So at the initial point you have zero conversion and F0 and C0, then you have the intermediate conversion X1 from the reactor of volume V1, then it goes into reactor of volume V2, that is your plug flow reactor, and you get the intermediate conversion X2, and then you finally go to reactor of volume V3 and get the final conversion X3. This may be a general case. Okay, in that case we just have to write down the individual design reactions to find the volume of reactors. So you can write E1 by F naught equals to X1 minus X naught by minus R1, because we have the MFR as a reactor 1. Okay, this is simply from the design equations of mixed flow reactors. For the PFR, you can write P2 by F naught equals to, since we have a PFR, we have a differential term. So integrating from x1 to x2 dx by minus r. This is for PFR 2. And then for MFR 3, again we can write V3 by F naught equals to x3 minus x2 by minus r. Okay, I should write minus r1 over there, so minus r2 and minus r3 to show the rate expressions separately. So this gives, sorry, this is for MFR, this gives the design equation for the three different reactors in series. Okay, if you want to graphically execute this procedure, let me draw the graph over here. So you simply plot conversion on the x-axis and minus 1 by r on the y-axis. Then you, let's say, get a curve like this one kinetics curve of the entire system. Then let's say this is conversion point x1, this is conversion point x2, and this is finally x3. Okay. So in that case, we have a mixed flow reactor first. So for conversion point x1, you will get, sorry, for conversion point x1, you will get a rectangle. From x1 to x2, you have a PFR. So you will just calculate the area under the curve, right? From the first rectangle, you will get V1 by F naught quantity. From the second area under the curve, you will get V2 by F naught quantity. These are all concepts from the design equations of the two types of reactors, plug flow reactors and mixed flow reactors. And for X3 conversion, you have to again draw a rectangle, but that starts from point X2. So this area of this rectangle will give you V3 by F naught. Okay. So in this way, you can obtain the size requirement for the three different reactors in series. And these intermediate conversions are very essential, especially because first of all they obviously help for the individual reactor sizing, and next thing is that if within reactors you want to put some you know, let's say heat exchanger, then to determine the heat duty of that heat exchanger, you need these intermediate conversions. So this comes very useful for such type of calculations in industry. Now, what is the best set of arrangement for ideal reactors? Okay, these are some of the observations that we note from the existing. best set of arrangements for ideal reactors. Okay, so what are these general rules? The most important rule is, if you have any nth order kinetics where n is greater than 0, the reactors should be in series. Okay, this is the foremost rule. Okay, in case mm, of you have n to be greater than 1. Okay, then this rate concentration curve, that is R versus C curve, this becomes a concave curve. Okay, concave curve means like this, concave kind of curve. In that case, your target will be to keep the concentration of reactant as high as possible. Okay, so concentration of reactant should be as high as possible in the system. Accordingly, you will be ordering your reactors. When you have n less than 1, then this R versus C curve becomes convex. Okay, that means it will look something like this. So in this case, the concentration of the reactant should be as low as possible. So accordingly, you have to order the system. Okay. To explain this, let us just refer to this example over here that we took, that we had three reactors in series. Okay. So if we had n greater than 1, okay, that is for the concave case, then we would order it as plug flow unit first, then small mixed, then a large mixed. This would be the order. But in case we had n less than 1, that is a convex case, then we would order it as large mixed, then small mixed, and then plug. This is how you would order the reactors in the system. Now, for reactions where this rate versus concentration curve goes through one minima point or a maxima point, okay, like it's not going to be so sharp, but if there is a minima or maxima point like this, then you cannot really follow these general rules. In that case, you have to determine the actual shape of the curve and then work out the conversion that you are desiring, the intermediate conversion. But whatever may be the case, when you are applying these concepts at a larger scale, the best thing to do is to study the rate versus concentration curve to understand the best arrangement of the ideal reactor units. That is it. Thank you.